Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. I think where we stopped last time exactly when I asked you what is remaining in this session to be done. What we have done so far is to define this objective function. Okay, we discussed in the previous lectures different ways to represent the loss function. If you remember, hinge loss and exponential loss and others. And we also, in the immediate previous lecture, we discussed multiple ways of representing the regularizer using LP norms. Now, if we assume that we have one loss function here and one regularizer here, how can we find the model itself? Okay, you remember at the end of the last lecture, I told you that I gave you the objective function, but I didn't tell you how to find the model, how to find the values that will minimize this function. So this is exactly the focus of this lecture, inshallah. Okay, so this is where we are. So the algorithm that we will study for optimization or for minimization in our case is called gradient descent. This is a very well-known optimization algorithm that is used with several machine learning models. One type of them is linear models, and you will also see that it is very widely used in neural networks, inshallah, when we will study neural networks in like a week or so. So what is the idea of gradient descent? Have you heard about gradient descent before in any course? You did? In optimization or what? What's the course? Numerical analysis. Type. So gradient descent in general is a general solution for our optimization problem. So this is the objective function that we want to minimize. We will use gradient descent to find the values of W and B that will make this function the minimum possible. What is the idea of gradient descent? Let's assume that I left you on some spot on a mountain or a hill, and you were blindfolded. You don't see anything around you. And I asked you to find the top of the mountain. What would you do? Yes. Go up. It's that easy, Yani? How can you know where is the up direction? That's the question. Gravity, how? That's the opposite, right? You want to go up. How can you reach the top? But you are, remember that you are blindfolded. You don't see.
The slope should be increasing, right? The level of the ground should be like
How can you do that? You will touch the ground around yourself, right? If you found the ground is going down, will you go into this direction? No. If you found the ground is straight, will you go into that direction? No. So you are searching for the direction where the ground will go up, right? Where the slope will be positive, will go up, right? That's exactly the idea of gradient descent. But instead of being applied on a mountain, it will be applied on a function. So if the function is like that, and you want to reach the top of the function, and you are starting, let's say, from here, so the value of the function is here, and you want to find the top of the function, then you will check around you. Should you go into this direction? Probably no, because that direction is the direction where the function is decreased. But that direction is where the function is increased, right? So you should go into that direction. And from the new location, you do the same. And then you do the same, and then you do the same, until you reach the top. That's the main idea. Let's talk into details. Here's again the idea. You start with a specific value. Remember that we want to find the values of the parameters, right? So here, for now, let's assume that we have just one parameter. So our goal is that given a function, like the function that is in red here, we want to find the value of the parameter that will make it maximum for now. Okay? For now, we will get the maximum. And you'll see that the minimum is very easy if we understand how to get the maximum. So this is the function. And we want to find the value of x that will make it maximum. And let's say that we are starting with this value, x0. Okay? What we will do, we'll start with this value. Then, at every step, we will measure the slope of the function, or the gradient of the function, or the derivative of the function. Okay? So if the gradient, so first, before we talk about this, what is the meaning of the derivative? And if I told you, I think you saw this many times before. You saw this, df by dx, right? What's the meaning of that? If I told you, that df by dx is 3, what does that mean? No, it's not the area under the curve. The rate of change. Okay, what do you mean by rate of change? Okay, we have a function here, f, and we have a parameter x. And this function is a function of the parameter x. Okay? When I say df by dx is 3, you said that's the rate of change, right? Rate of change of what? Of the function with respect to x. So that means that if I increased x by delta, you see that I increased the x by delta, what will happen to the function? What will happen to the value of the function? Let me make it. df by dx equals 3. So if I increased x, so x, I increase it by delta x, what will happen to the function f? F, so it will be the value, the previous value, plus 3 times delta x. Very good. That's the meaning of the derivative at specific value of x, of course. Okay? So that's important to understand here, that when we compute the derivative, it's not just an equation that we memorize how to do it, right? The meaning of it is that if we changed x, how the function value will change at that point. So here, if we changed x a bit here, then the function will go with that increase. We call this the derivative, and if we have multiple parameters, we call it the gradient. Okay? So if I want to change x in the direction when the function increases, what should I do? I should compute the derivative at the value of x and then add that, or add part of that, to x. Yani if the gradient is positive, should I increase or decrease x? In this case, the gradient is positive or negative? Positive. So I should increase or decrease x? Increase x. Okay, increase x. Type. How much? It should be a function of how the gradient is. If the gradient is very large, I should go with maybe big step. If the gradient is small, then I should make small step. Okay? So, in the next step, after computing the gradient, I will update x. So, x will be equal to the old value of x plus the gradient. But to control how much the step is, I will multiply it by what we call step size or learning rate, We call it step size or learning rate. Okay, so maybe this is just 0.1 out of the gradient value. Okay, طيب. If I do that once, did I reach the top of the maximum of the function? No, so I have to repeat that. As you see here in the figure, I will get x1 from adding the gradient at x0 times the learning rate. I will get a new value of x. Then I can now compute the gradient at x1, and then from that I get x2. Then I compute the gradient again, get x3, and so on. So that's an iterative algorithm. In every step, I change the value of the parameter in the direction of the gradient. Why in the direction of the gradient? Because that's the direction that points to increasing the function. Okay? That's if I want to maximize. But what if I want to minimize? I will go to the opposite direction of that. Because the opposite direction of the gradient is the direction where the function will be decreased. Okay? So that's why this update statement is called gradient ascent. Because I'm maximizing here. But gradient descent is when we minimize. So we'll go in the opposite of the gradient. Okay, so instead of plus here, find that we have minus here. Why is it minus? It's going in the reverse direction of the gradient. Because the gradient points me to where the function is increasing. But I want to actually decrease the function. Okay, so I will compute the gradient and then subtract it to get the new value. Yes?
Like we would stop with x4, the gradient is smaller than x.
We'll discuss the stopping criteria. Okay, we'll discuss it today, inshallah, later. But let's assume that we will go in some steps. Okay, go through this in some steps.
Yeah, because I was wondering, like, if we stop like identify just the local maximum, but then we say local maximum.
Yes, we might find the local minimum, but that's why we said that the function should be convex. If the function is not convex, it's not guaranteed to find the global minimum. Okay, is that clear? So what is the main idea here? We have a function and we want to minimize that function. Okay, and we'll do that iteratively, step by step. We'll start with a specific value, and then we do these two steps in multiple iterations. We compute the gradient at that value, then we update the parameter, then we compute the gradient, then we update the parameter, then we compute the gradient, then we update the parameter, and so on, until we reach the minimum. Or we do a specific number of steps. This is what we call gradient descent. It's very simple, but I hope that you got the idea. I had a question that I wanted to ask, but I forgot. Do you have any questions? Right, let's continue, and I think I will remember the question, inshallah. Right, so this is here the main idea is to take iterative steps to update the parameters in the direction of the gradient. So in every step, we need to see where the direction of the gradient is, go in the opposite of that direction because we are minimizing, and then continue. So in every step, compute the gradient and then update the parameter. Okay? Right. That's what will happen in one dimension. So this is very similar to what we saw in the previous slide, except that this is now in the minimization example. Okay? So if we started here means that we start with this value. So here we assume that we have just one parameter. Okay, in one dimension means that we have just one parameter. By the way, how many parameters we have in a linear model? Two. What are the two parameters? The weights and the bias. Is the weights one value, one parameter? The number of features. Very good. Okay, very good. The number of features that we have. Okay, so if the number of features is k, then we have k plus 1 parameters here. Okay, but just for simplicity for now, let's assume that we have just one parameter. So our goal is to find the value of that parameter that will make the function that we want to minimize minimum. Okay, so we start with one value. Let's say that this is W0. Compute the gradient. Now, if we compute the gradient here, will it be positive or negative? Positive, of course, right? That's gradient is positive here. And that's why we go in the reverse direction. Okay, so that's the reverse gradient. That's the opposite, the inverse gradient. So the next value of W should be to the left or to the right? To the left. So the next value should be probably here. Then we compute the gradient again. Okay, again the gradient is positive, so we'll go to the in the negative direction, right? So the next value will be probably here, and so on. So the actual values are the values of the parameters, but the values that we are minimizing are the values of the function. That's the blue curve here. So this is the function, this is the parameter. Okay, is that clear? Of course, this is an ideal case when the function is nicely convex, so we will reach the minimum after some steps. Okay? Type. What if we have two parameters, not just one? It will be more complex, right? Type. Here, what are the axes here? We have just one weight. Let's say that we have just one weight, W, and the bias. Type, what is the third x here? That's the function itself, the value of the function itself. Like here, right? We have, in one dimension we have the parameter, and the other dimension we have the value of the function itself. Here, the value, we have two parameters, and the z-axis here is the value of the function. Type, where is the minimum that we want to reach? Is this point. Okay? Type. How many parameters we are changing here? Two parameters. Two parameters, not just one. So we have to update every parameter. Type. Do we have just one gradient here, one derivative here? We have a partial derivative of j. The function here is called j. Okay? So we have partial derivative of j with respect to w, and we have a partial derivative of j with respect to b. What is the meaning of each? It's the rate of change, right? So this is how much j will change if w changes a bit. And this is how much j will increase if b changes a bit. Okay? So when we update w, I think this would be very tight to me, so let me erase everything and write it again. By the way, this is as a vector, it's called the gradient. Okay, so the gradient is the vector of partial derivatives with respect to every parameter. Okay, type. Type. Now, we said that we need to update two parameters, right? So w will be updated like that. W will be the old value of w plus or minus the learning rate times the partial derivative of the function with respect to w. Same here. b will be the old value of b minus eta, the learning rate, times the partial derivative of the function with respect to b. Okay, so we have two different derivatives because we have two parameters. Type, if we had one parameter only, will the derivative change with the change of the value of the parameter or not? Generally it changes, of course, right? So if we go back here, for example, the derivative of the function at that point at x3 is almost 0, right? But the derivative of the function at x1 is positive. So of course the derivative will change. Okay? So every time we have to compute the derivative value. Okay? With respect to every parameter. Any question about this? So in every iteration then, in gradient descent in this case, we'll have to get the gradient with respect to w, change w. Get the gradient with respect to b, change b. That's one iteration. And then we repeat that. Okay? Is that clear? Right. Here is the pseudocode of the algorithm. Gradient descent takes the function that we want to optimize. That's general, by the way. Yani any function. That takes any function. As long as the function is, it doesn't have to be convex, by the way. It's being convex will make it easier to find the minimum. But the function doesn't have to be complex. But the function has to be differentiable so that we can compute the derivatives, right? If the function is not differentiable, then we will not be able to compute the derivatives, and thus we cannot update the parameters. Okay? So the function is a parameter here, is given. Then here we get a constant number of steps. Say, 20 or 30 steps we want to update the parameters, and then the step size. For now, let's assume that the step size is constant. Type, how the algorithm works, we start with, forget about the superscript for now, okay? Don't look at the superscript. Z here is the vector of the parameters. So initially, all the values of the parameters are zeros. Then we go through this loop. How many iterations in this loop? That's the number of steps here. Okay? Right. Now let's look at every iteration. What are we doing? Just the two steps that we discussed earlier. Let's assume for now that we have just one parameter. So z is just one value. We will compute the gradient. So this is the symbol for gradient of f with respect to z. Z is the parameter. Okay? That's the gradient. So we'll update now the parameter with the old value of the parameter minus eta, which is the learning rate, times the gradient. That's it. That's what we saw already, right? Any question about this? Type, if we have more than one parameter, what will happen? No, we either repeat these two steps for every parameter, and if we have 3 parameters, then we have these 2 steps for every parameter. Okay, so for Z1, Z2, Z3, or if the language that you are using allow you to do the vector operations like Python, then this will be just one line. Every line here will be just one line, assuming that you already computed the derivatives. Okay, but this is actually, in general, it's a loop by itself. Loop over all the what? The parameters. All the parameters. Okay, this algorithm, by the way, is very general. It's general. It's not only about linear models, by the way. Okay? It is very general. Any function that has parameters, this algorithm will try to find the values of the parameters that will make this function, that will get us the minimum value of that function. Okay? So in general, this is any function, by the way. But in our context, this is the optimization function that we saw in the beginning of the lecture, the long one that has the loss function plus the regularization. This is, as a whole, is the function that we want to minimize. Okay? Is that clear now? Type. But this pseudocode in particular, it's not only for that type of parameters, of functions. It takes any function. As long as this function is differentiable. We can compute the derivatives of the function with respect to every parameter. Okay? Type, what is this? What's this, Mariam? That's how many updates we will have for the parameters. And in every iteration, we make an update. That's an input, yes. In our terminology, in the lecture, in the course, this can be a hyperparameter. Okay? But for this algorithm, it's just a constant. It's just an input. And how about this one? Step size, which is which controls how much we will update the value of the parameters. So we initialize the all parameters, all the values of the parameters, and then we make the updates. Before we go again into the details of this loop, what is the outcome of this algorithm? No, it's not the function. Huh? The values of the parameters. That's why at the end, you see here, return what? Z. Z is the vector of the parameters. So the values that we reach at the end of the loop, that will be the values that we will return back. If we are talking about linear models, then this should be the weights and the bias. Okay? Type. What will make this function give us a linear model? And we said that this algorithm takes any function, right? And this function is a function of some parameters. So it will give us, at the end, the values of these parameters. Type. Now, in the context of linear models, we want to give the algorithm a function of the parameters of a linear model. So the function has to have the weights and the bias. So the loss function has to be a function of the weights and the bias, and the regularizer part of that function should also be a function of the parameters. Okay, so that at the end, this function is actually the function that will provide us with a good linear model at the end. Okay, so at the end of that, of the execution of that algorithm, it will return to us the values of the weights and the bias. Right. Back to how the algorithm works. So this is the initialization step. All the values are zeros. Then we need to update. We need to update the values of the parameters. Okay. So we'll do that in k steps. In every iteration here, we have k iterations. In every iteration here, we will make one update per parameter. How can we do the updates? We have to find the derivative of the function, because that's how we will update the value. We'll update the value in the direction where the function will decrease. Okay? So we have to compute the gradient first, and then use it here to update the value of the parameter. Okay? We'll have to do it for every parameter. It depends on how you want to implement it. Okay? In general, this has to be repeated for every parameter. If the language allows you to do it in a vector operation, in one line, fine. Type, what is the condition to do this? I mean, to be able to do this, to be able to do these two lines, what is needed? of course, g will change, right? But to compute g, we have to compute this, right? G is the derivative, right? So we have to know how to compute actually the derivative of the function with respect to every parameter. Back to calculus courses. Okay, given a function, you need to know how to get the derivative of that function with respect to specific variable. It's not called, I think, parameter in calculus. It's just called a variable, right? Yes.
What I understand is that when we're using gradient descent, we have to keep computing the derivative until we reach the minimum. So the gradient descent has to be negative at every step. The moment we get the descent, the gradient to be positive, we shouldn't update because we'll be going upwards then.
No,
But
no,
there's no if statement.
no. We update, but in the reverse direction.
Okay,
No,
so
always the derivative is pointing to the direction of increasing the function.
yes.
Okay, so we should always go in the reverse direction.
Yeah, I get it. We go in the reverse direction.
Yes.
But after we reach the minimum,
ما احنا we didn't yet talk about when should we stop. In this simple algorithm, we said that we will take k steps. Okay. In the next slide, if we will, يعني have time, inshallah we will, we'll talk about when to stop. Yes.
So that one I initialized with 0.
Why did we initialize with zeros? Arbitrary choice. Yeah. There's nothing specific. When we talk about neural networks, we will change this a bit, okay, for a reason. But here you can start anywhere. The simplest thing is to start from 0. Okay. Any other questions here? Type 1 last thing that I told you to forget about in this slide is the superscript. What is the superscript here? The superscript here indicates the number of iteration only. Okay. Without it, I think everything is clear, but it's just indicating the number of iteration. Okay. So K here is actually the index of the loop. Type. Before we talk about when to stop, let's talk about the step size. By the way, if you looked carefully about on this algorithm, you will find that even the step size or the learning rate is has a superscript k, which means that it can change over iterations, or it's actually different. This is input. Usually it can be used as a constant, but in general it can change. You can give it actually to the algorithm so that in iteration number 1 the step size will be like that, and iteration number 2 will be like that, and so on. Or it can dynamically change, as we will inshallah talk about in neural networks. Now let's assume that the step size is constant. If the step is very small, it will have an effect on when can we reach the minimum. And also if the step is very high, it will have an effect. As you see here in the figures, this is when the step size is very small. Okay? That means that we are taking very small steps in the direction of the decrease of the function. We can do that, but that might make our optimization to be very slow, because we are taking very small steps until we reach the bottom of the function. It will take a long time. Okay, let's see the other extreme. In the other extreme, we might do something like this. Because the step size is large, we can go from this point. So let's say that this is the starting point. If the step size is large, then we might go to this point. And then this point. And then this point. And then this point. Okay, you see there is an oscillation in the value of the function and also in the value of the parameter. That might also make it very slow to reach the minimum. Okay, so the step size actually has a huge effect on the time that it will take us to find the minimum. So the gradient descent is actually sensitive to the step size. So there are many algorithms that some of them we will inshallah study when we talk about neural networks on how to control the step size. One rule of thumb when we use the learning rate is to start with large step sizes, and then over time we decrease it. So we start like excited about changing or finding the minimum, and then when we reach the minimum, we should pay attention to the small details, and we should not make big steps so that we don't overshoot the minimum. Overshoot here means we can even go beyond the minimum, okay, or miss it. So that's the impact of step size. The last thing that we want to study in this lecture is when to stop. So in the pseudocode that you saw, it was just constant number of iterations. But what should be a better criterion? When should we stop our updates? In other words, when can we know or we can think that we reached the minimum of the function? If g is 0, sometimes it's not exactly 0, but maybe it's close to 0. So if the gradient is close to 0, we can stop. What more? You mean, but if the gradient is positive, doesn't mean that we reached the minimum.
No, that means we went up again, so we can go to the next step.
But before that, we should reach something close to 0, right? Okay, so this is already covered. What else? How about the values of the parameter? If the value of the parameter stop changing a lot, then probably we can stop. Okay, what else? Any other ideas? How about the objective function itself? Remember that we are minimizing a function, right? How about the value of that function? That's what we want, right? But we don't know the minimum. But if that function also, the value of that function doesn't change a lot, we might probably assume that we reached the minimum. Okay, so there are many ways to stop. So when the gradient gets close to 0, we said it. When the objective stops changing much, that's what we just said. When the parameters stop changing, we said it. Or the last one here is to do it but using a diff set. Remember 3 or 4 years ago when we talked about development set? Why do we need to use the development set? To optimize, right? To find the best values of the parameters. So we can also stop when we reach a good performance on the development set. Remember, with every update in the parameter, are we changing the model that we are learning or not? Are we changing the model? Where is the model? It is the parameter. The parameters are the model. So when we are changing the parameters, that means that we are changing the model, right? So with every change of the parameter, we can check the performance of that model on the development set. Okay, and we stop when we get a good performance. So all of these are criterion to stop. Inshallah, next time we'll see how to choose the step size.